Now with this theory in mind, we can state the sufficient condition for existence of Laplace transforms. For this we make a definition, and this is about functions of exponential order. So this definition says that a function ft from 0 infinity to r is of exponential order if there exist constants alpha, positive alpha, m and t naught positive, such that the modulus of ft is bounded above by m e to the power alpha t for all t greater than or equal to t naught. So this definition imposes a growth condition for the function ft for large values of t. It says that it cannot grow faster than some multiple of an exponential function. So we will see that once we have this kind of once we impose this kind of growth condition on the function, the Laplace transform will exist. So let us state this as a theorem. Suppose that f from 0 infinity to r is piecewise continuous on every interval 0 to r and is of exponential order, then the Laplace transform exists. Then the Laplace transform of f exists. Okay. So this proof is quite easy. So we have to show that the Laplace transform of this function ft, which I denote by fs, which is 0 to infinity ft exponential minus st dt, this should exist. So by definition, this is again the limit r goes to infinity 0 to r ft e to the power minus st dt. Now because f is piecewise continuous on every interval, this function, the multiplication of ft e to the power minus st, will be piecewise continuous on every interval 0 to r. This is a piecewise continuous function on 0r, let's say for s positive. Okay. So first note that it suffices to show that the integral 0 to infinity with modulus of ft e to the power minus st dt exists. So we are claiming that if you just show this for the function ft e to the power minus st replaced by the absolute value of the function, then as a consequence we can infer that the original integral also exists. So This is because of the following lemma. I'll state it as a result, which says that for f, a piecewise continuous function, on the whole interval 0 to infinity, if the integral 0 to infinity mod ft e dt exists, then integral 0 to infinity ft dt exists. So, just as a terminology, in such case the function ft is called absolutely integrable. So let's see the quite easy proof for this statement. So we begin by noting that we have the inequality minus ft less than or equal to ft less than or equal to minus modulus of ft is less than or equal to ft is less than or equal to mod of ft for any t greater than or equal to 0. So then this implies is the same thing as writing 0 less than or equal to mod ft plus ft is less than or equal to 2 times mod ft. Just adding modulus of ft on both the inequalities, we get this inequality. And now we know that integral 0 to infinity modulus of ft dt exists. So this implies that integral of 0 to infinity modulus of ft plus ft, this exists dt, this exists by the second theorem of sufficient condition above. So we have seen that in this case we have, this is our gt and this is our ft. Well, I'm not going to use the same notation here, but let's call it capital FT. So capital FT is positive and it is bounded above by an integrable function gt. So therefore capital FT is also integrable. So this we wrote down as a theorem for a sufficient condition for the existence of improper Riemann integrals. So we have that this integral exists, and now I'm going to subtract. So this implies that integral 0 to infinity modulus of ft plus ft dt minus integral 0 to infinity modulus of ft dt, this also exists, because now it's a difference of two finite things, therefore it must also be finite. And now I can use the linearity property to get that the modulus of ft dt also exists. So as a remark, notice that we cannot write, so why we did all this trickery with the modulus of ft plus ft, which is this fact here which says that we cannot write that the modulus as of the limit as r tends to infinity 0 to r ft dt is equal to limit r goes to infinity modulus of 0 to r ft dt. We cannot write this because we don't know yet whether this exists or not. We don't know whether this exists. So we are trying to prove that this exists, and we cannot use this interchange of modulus and limits unless we know that both limits exist. So this formula is only valid when both limits are known to exist. So therefore, we had to do this trickery with inequalities and using the comparison theorem for convergence for the existence of improper Riemann integrals for positive functions. So here also another warning is that we cannot use 0 to infinity ft dt is less than or equal to integral 0 to infinity mod ft dt unless we know. So we cannot use the inequality, this inequality, unless we know this exists. We already know that this integral exists. So I saw in some books that this has been written, and it's unfortunately incorrect, because we don't know whether this this integral inside the modulus exists yet, so we cannot write this inequality. So now we go back to the proof for the theorem. We just have to prove that integral 0 to infinity modulus of ft e to the power minus st dt. I can take e to the power minus st outside the modulus because this is always positive. But now note that this is the limit as r goes to infinity, integral 0 to r modulus of ft e to the power minus st dt by definition. This is less than or equal to limit r goes to infinity, integral 0 to r modulus ft e to the power minus st dt. Since this is always positive, the modulus will not affect it. And now we use the fact that ft is of exponential order. So this is 0 to r m e to the alpha t e to the minus st dt. Okay, and this is limit as r goes to infinity. You can take m outside the integral, and then you get e to the power minus s minus alpha times t dt, but this limit can be easily evaluated and you just get m by s minus alpha. So provided as s is greater than alpha, so you want this to be positive, this coefficient s minus alpha to be positive, this is equal to m by s minus alpha. Therefore we get that the modulus of fs is less than or equal to m by s minus alpha for s greater than alpha. Therefore fs is finite for s greater than alpha. So the Laplace transform exists in the region s greater than alpha. Now whenever we write the Laplace transform of a function, we should always mention the region where it is valid. Here the region of convergence is s greater than alpha, but we should always mention what is the region in which the Laplace transform is valid. So what are the examples of functions of exponential order? So first is ft. It can be any power of t where n is a positive integer. This is of exponential order. Secondly, ft if ft is a bounded function, then it is of exponential order. Then ft is of exponential order. Third is any polynomial in T is of exponential order. So, by the way, in the second example, you have all the trigonometry functions like sine and cos, because they are all bounded functions. But from the first one, since all powers of t are of exponential order, then any polynomial of t is also of exponential order, and here we are using that if two functions are of exponential order, then their sum is also of exponential order. Another example is log of t, log to the base e. This is of exponential order, simply because log of t is less than or equal to t for all positive t, and since t is of exponential order, then log of t is also of exponential order, which means that if f and g are two functions, f is less than or equal to g and g, this is of exponential order, this implies that f is of exponential order. So we have used this fact here that ln t is less than or equal to t, and we know that t is of exponential order. Therefore, log of t is also of exponential order. Now let's see an example where a function is not of exponential order. So this is a non-example. So first is, let us say ft is exponential of t square for all t positive. Now it can be checked that by taking logarithms that this is not of exponential order. We can produce new functions from this function ft which is not of exponential order. For example, if ft is not of exponential order, then exponential of ft is also not of exponential order. So one can have many examples of functions which are not of exponential order, but note that our condition is only a sufficient condition for the existence of Laplace transforms, and there exist functions of which are not of exponential order which also have for which the Laplace transform exists. So it is only a sufficient condition but not a necessary condition. So now that we have some theoretical background for the existence of Laplace transforms and existence of improper Riemann integrals, let us go back to the computation of more functions, computation of the Laplace transforms of some more functions. So let us compute the Laplace transform of more functions. So the first one is ft is e to the power alpha t, where alpha is positive. So note that this is now a function of exponential order, so its Laplace transform will exist. Now let us compute it 0 to infinity. So this is fs 0 to infinity ft e to the power minus st dt. This is 0 to infinity exponential alpha t minus st dt, and this we have computed before. This is 1 over s minus alpha for s greater than alpha. Okay. So the Laplace transform of e to the power alpha t is 1 over s minus alpha for s greater than alpha. Now let us consider ft is sine of t for t greater than or equal to 0. So fs is integral 0 to infinity sine t exponential minus st dt. Now we will again employ integration by parts. So I take u to be sine t and v to be exponential minus st. Then you get this 0 to infinity sine t exponential minus st dt. This is equal to, so let's evaluate this by integration by parts. So the first term is sine t exponential minus st by minus s 0 to infinity minus integral 0 to infinity cos of t exponential minus st by minus s dt. So let's see what the first term is. At infinity this goes to 0 because sine t is bounded above by 1 and exponential minus st will go to 0. So you get 0, and at 0 you again get 0 because sine t will be 0. So you get a 0 here in the first term, and then you get a plus 1 over s integral 0 to infinity cos t e to the power minus st dt. Okay. Now I am going to apply integration by parts one more time for this Laplace transform of the cos function. So 0 to infinity cos t e to the power minus st dt. Now let us evaluate the Laplace transform of cos t. Then we can again employ integration by parts. So you will get e to the minus st over minus s 0 to infinity minus integral 0 to infinity minus sine t e to the minus st over minus s dt. And here at infinity the first term is going to be 0, but at 0 this is going to be 1, and you have a minus s, and here you will have 3 minus signs, so you get a minus sign outside, 1 over s integral 0 to infinity sine t e to the minus st dt. So in the end we get 1 over s minus 1 over s integral 0 to infinity sine t e to the power minus st dt. Now I am going to plug this in the equation that we found before. So fs, the Laplace transform of sine t, this is equal to 1 over s integral 0 to infinity cos t e to the minus st dt, and we can plug the value of this Laplace transform of cos t, which is 1 over s minus 1 over s, and the Laplace transform of sine t, which is again fs. So now we have this equation for fs on both sides. So we can solve for fs. So you get fs 1 plus 1 over s squared equals 1 over s squared. So you get fs is 1 over s squared plus 1. So you can have s greater than 0. So this is the Laplace transform of the sine function. But now that we have computed it for the sine function, we know how the Laplace transform of sine and cos are related. It is just 1 over s times the Laplace transform of the cos function. Therefore, the Laplace transform of the cos function is just s times the Laplace transform of the sine function, sfs, which is s by s squared plus 1 s positive. So we have computed the Laplace transforms of some more functions, and we have also looked at the existence criteria for the Laplace transform. In the next lectures, we will see some more properties of Laplace transforms, more theoretical properties, which will help us to compute the Laplace transforms of even more variety of functions.